Let's take a look. So the first one here, the display list. Right here, the main thing is, in the first one, what we did is we traveled through our node to find the end of the list, so we could add a new item to it. In the display list, we want to make sure we print every item in our list out on the line, at least get this. If we think about it, what we want to do is we want to make sure we travel, we touch every node in the list, and just in this one where we went through and just said, hey, as I go through the list, just move to the next one until I get to the end. And this one we say, I want to go through the list, but as I go through the list, let me print as I go until I get to the end. And so for all intents and purposes, the main thing we're going to do here, first off, let's make sure, void node, no, static void, is I can start with this. I don't know where this. So there's two ways you can approach these, by the way. You can do a, let's do this first. Let's do this one. So first, we'll do the traveler. Main thing first, traveler. So integer trav equals head. Do the while trav dot next is not equal to null. We'll do the same code we had above for now. Like that for the moment. And so from here, though, now the main thing is how do we print the stuff? The simplest version, of course, and would result in this is to just do the sout print and do trav.val. This is going to give us the value. The main trick to this, though, again, and this is something that you guys saw with me in the beginning that isn't on the video, so make sure it's clear, but we saw this with Sergio as well. The main trick for this one is making sure that we print actually every single node as we hit it. And this is going to be interesting with while loops. For while loops, unlike with for loops, for example, we could change it differently. With while loops, there's a problem of either missing the first or missing the last, especially with looping structures like this, where when we hit this item, we're not what we expect. And so there's two ways to fix this. Either one, we can do sout again, print trav.next, trav.val, sorry, value. That's one way we do it. Another way actually is we can change this instruction here. Remember, trav is a node, and what are the two things that the trav can have? What are the two values that a trav can be, or states, I guess, or what can trav hold?
Index and value?
Not quite. Not what I was looking for. I'm trying to make sure I asked the question right.
Or the pointer.
A pointer or kind of, hold on. Trav can be what or what? There's two things trav can be.
A value or null?
There it is, right? It can either be a node or null. That's the key thing there. It can either be a value, a node, or null. And so one thing we can also do here instead is I could also just do while trav is not equal to null. Instead of saying that next is not equal to null, I could say when trav is not null. While trav is not null, that means I'm on a node and I can print. As soon as trav is null, I can't do this. This is now not allowed. This is the simplest code that allowed me to print every single item in my list. Of course, I didn't make it where you had to do this version because I know that you're trying to reuse kind of code from here. This is just showing that slightly a little better. This is kind of the difference between and whenever I played baseball when they're younger, you hear the coach say, move your hands closer together. Both ways you're going to hit the ball, but as soon as you move your hands closer together, you're going to hit it a little better. This is that concept there. This is just being a little bit nicer on your code because then I don't need that extra system out. Does that make sense? Because this one, I'm going to hit every single node. I'm going to start on head, which was 2, with the next being 8. I'm going to go move trav equals trav.next, which is the 8 node. I'm going to go, it's going to pop back up since it's the 8 node, trav is not null. So I'm going to print the value, which is 8. I'm going to then move to the next node, which is the 5 node. So trav is not null, it's 5. It's got the 5 node in it. So I print out the 5. I move to the next one, so that's the 9. I go back up. Trav is not equal to null yet. It's 9. It's on the last item, but we are a node still. Trav is still a node. And so we print out the 9, and then we say trav equals trav.next. We know trav.next, since 9 is the last item, is null. And so we say trav is equal to null now. We set trav to null on purpose, for all intents and purposes. We set it to null. And so then we check and say, hey, oh, we're null. We're not in the list anymore. We're out of the list. We're done now. See how that works? See how that process goes? Did anyone else actually figure this one out? Cool, I was still able to show something different to all of you. I'm still doing my job as a teacher. Yay. That's the key thing. Like, that's one of the other things as well. As long as you got the version like that we showed before, where you do the trav.next not equal to null, and you either print the head above or you print the last node before, that's fine. Because again, I said it before, I just want a valid output. To show that this works, I'm going to go ahead over here and do display list head. Save it. We'll run it. We'll see the 4 trues and then our display. And what did I do? Oh, right. This guy. Mark that as a return a node integer. So I'm going to comment him out for the moment. There you go. So you have that one. For the additional challenge of this comma-based situation here, this is where I like to use like string builder or just at least an output string where I can build an output. And so I usually like to do output with a string. Empty string. I can do S out here. Output. And what I would do in this case is, yeah, I'm going to first do, instead of that, I can switch this now to output plus equal trav.value. I'm going to do a quick if trav.next not equal to null. Put equal space. Do we see how that's going to do it? Can you see that forming in your head? And that's one of these, another technique that for me really benefits me, is I can very much focus on just what I'm working on and kind of run through a couple examples of the flow through my head. And what I visualize in my head is I see, okay, yep, first time through, I get the 2, and then it's not null. The next item is a 5, 8, so it's not null. So I'm going to get that comma space. And I'll do that like to just know that I got a space there. And then I'm going to go move to the next. I'm going to move to the 8, pop back up. I'll print out the 8. The next one's not null, so I'll get that comma. And then I'll ask myself, well, if I was on 9, so I'm not even going to do the 5. I'm not even going to do the 5 because I'm like, you know what? I'm on the 9. Let's see, will the 9 work? I'm going to add the 9 to my list. 9 next is null, so it's not going to add this to it. It's going to move to null, and then it's going to fail out and it's going to drop out and print it. So I'm going to get that output that I want to get. And so this is something that I'll do in my head is I'll walk through, so I'll kind of look through the code in my head and try to visualize what's happening to my variable, my main variable, my output variable. I'm not necessarily visualizing the trav variable from next. I'm aware of it, but I visualize in my head what's happening to output. It can help me to really visualize what I'm trying to get done. Let's see if that worked. Got our nicely formatted list. Just, this is where it's asking you to do a string builder. Because we're doing concatenation in a loop, they recommend string builder. So just to show that looks like, we'll see that there. And then we go from a output equals new string builder, output.append, output.append. So, when doing a looping structure, it is best to do string builder. It's just better for memory. You can always start with the output string first and then switch it over after. It's fine. Any questions on this guy? Cool. And so yeah, my main goal of the display list one was to remind you guys that we can do a while not equal to null variation of the traveler loop. So these are the 2 main versions of the loop. The while trav.next is not equal to null, and then the while trav is not equal to null. So those are the 2 variations of the loop where you want to make sure that you are going through the entire list, but you don't want to pop out the second you find that last one. You still want to do stuff on the last one. That's the negative. That's the problem with this one, is that this one will not do anything to the last node. It's not going to validate anything. It's not going to check anything. It's just going to move you through the list, and as soon as it finds the last node, it's going to pop out of the loop. And so it's not useful for if you need to do something to every single item in the node. This is the useful one where you need to go through the list all the way to the end, but also do something on each node. Do some sort of logic or some sort of items on each and every single one. Sound good? Cool. So now that, let's look at this one. So the find item. Let's review again. So in the add node, we want to go through our list to get to the end and then add a new node to the end of it. So we got to travel, we got to go navigate all the way to the end of our list and put a node on the end. In this one, we want to navigate through our list on every single node. We want to print out that node's information and potentially some formatting. All right. On this one, what do we want to do? In that same kind of way I described the other two. One sentence. What do I want to do on this one? Anybody?
We want to traverse through the list and return the first node that which values matches the query.
Yeah. We want to go through our list, and as soon as we find one that matches, we want to return it or return nothing. And so we can see that similarity between the other ones, right? We still say that first initial part of want to go through my list. I want to go through the entire list. We still have that similar concept there. So we can do that same kind of starting behavior of node integer. Trav equals head. Oh, right, because I don't like the word trav. Trav's not a word. I'm not spelling out traveler. That's a word that I will definitely make a mistake at some point, not notice it. We got our traveler. And this is again, now is this another one where we're looking for the last node, or are we going to go through until there's nothing left? We want to go through and check every node to see if it's my query, right? So again, if I was to do,
Yeah, we
what's
have
that?
to check every one.
Yeah. So again, if I was to use the other one we use, the while trav.next not equal to null, we'll have that same problem with the last node. That in here, what we're going to do inside a loop is the check if node has our query, right? We're currently going to check if our node has our query. Not good, because this one won't check to see what's what I'm trying to say. So this is not gonna check the last one inside the loop, because as soon as we get to our last node, it's gonna break out. Remember that the trav.next moves to the last element, but on that last element, it does not run what's in the loop, and that's the catch. That's the logical error of this looping structure here, this loop for the traveler. Is that you can run into that annoyance there where then in that case, if I do this version of it, I'm going to have to add the exact same code of my while loop down here to do a final check. Final. And a little note I'm going to add up here. Trav.next. Node. Not from the last node. That's not equal null. Yeah. All nodes. Object. All. Make sense? Got that. What I'm going to do here now is check if our node. So now we're going to switch this to, yeah, trav not equal to null. So you don't want to have to do a final checkout here. We want to make sure our looping logic is going to check. And as soon as it finds it, it'll return it. We'll do if value equal query. What do we want to do? Pretty simple line of code. What is it?
Return Trav.
Yeah, return Trav. And if we get to the end of the node, if we get to this line here, 59, what does that tell us?
We haven't found it.
Yep, and Trav means Trav is null. We don't have any data to check, so we don't have to check Trav here, right? Trav is null. No additional checks. So what can I do here then? I need to still return something. What do I need to return? What do we return if we don't find it? What was that?
Return null.
Yeah, return null. Other than some of you having that little additional check at the bottom, is this kind of what you got going on here? Similar?
Yeah, and it's still not working for me.
Really?
Hold on.
Well, don't you
Oh,
need
no.
to go through and make trav.next?
Like in my.
I didn't do that yet. You're right. I didn't do that yet. Trav equals Trav next.
I thought you were doing that on purpose.
Oh, okay.
Nope, I was not.
See, I was. That's the line,
I missed a lot of code.
and
Nice
that's the line I
catch.
was missing.
Totally did that on purpose to you guys to mess with you now. Wanted to see if you caught that. I actually was not done though. There's actually more I can do to this still. So hold that impressed for a second. Because right now we have a while and then an if statement. All our while is doing is then running a initial if. While Trav is not equal null and Trav dot value not equal query. Remember, if this comes back true, it will not test this. So as soon as I have a null item, I will not get the error of value being invalid on a null because it will not check this. What that allows me to do is now just return Trav. Because as soon as Trav is equal to the query, it won't move down and the Trav is now the query, so I can just return Trav. Did I get the impressed?
I'm mad because I was so close.
Oh, I hate when that happens. Yeah, but at the same time, it's like you should feel confident though that you were that close. So be proud of the fact that you are close. If you never get close and can always figure it out, then you don't need to be in class. So be happy that you were close.
I have a question.
Go for it, Mike.
Is line 53 necessary where you reassign? Well, you assign Trav to head. Could you just do head instead of Trav?
Well, again, we are moving it. And so if we do that, we're going to lose, the head will be lost. I'm pretty sure it's a pass by reference, not a pass by value. So this isn't a copy of head, this is head. And so if I was to change this, it will permanently change the list. And so this is something you want to be aware of when dealing with complex items like this. There's a concept of pass by value and pass by reference. We can definitely test to see what's happening here. But I want to show you this little image here. Pass value versus pass by reference. Get out of the way, Zoom. Please move out of the way, Zoom. Thank you. So this is the concept of pass by reference
One of them's
versus
a copy.
One's pass by value, one's pass by reference. When you pass by reference, whatever you do to the item inside of the method will actually affect the original item and will affect it outside. And that's considered a destructive method. So if we make changes to head, if it's a pass by reference, any changes we make to the head will affect the head in the main method and actually change our list. A pass by value, usually what happens when you pass an integer or pass a value for like mathematics, if we change that variable that's a parameter of the method inside the method, it will not change it. It will not affect the original item. This is something you need to, that is different based on each language. So knowing the difference between each language is not something you can rely on. A lot of times it requires you to just quickly test, see, am I getting a reference or am I getting the actual item? A lot of times if you're passing a pointer of some kind, then it's most likely a pass by reference. Because these are classes, and when we print this, we get a reference value, it is very likely a pass by reference. but we can always check it. So we could check it by saying, you know what, let's not make it in trav. Let's change all of these. I'm going to reassign this. So we'll do refactor, rename, head. Okay, it guessed. Nice. Cool. That's new. So I just renamed everything head. You don't have to do this to yours if you don't want. What I'm going to do quick is I'm going to run a finder. So let's do a find. I will find 4, 5. We'll find 5. And then we will go ahead and why is it yelling at me?
You gotta pass
Finding
head
the
in
head.
first.
Yep. Thank you. And 5. There we go. We'll do that. It's going to return a node. So we'll go ahead and do a display list. So display. And so what this will actually end up doing is it's going to actually print 5, 9. Because display list, and we're using 5 as our head of our display list node. So it'll print 5, then 9. So this is going to print 2, 8, 5, 9. This will print 5, 9. And then what we're hoping is that our display list will go back and display 2, 8, 5, 9 again. If it does, we'll do this. If 2, 8, 5, 9, then it's pass by value. If it's 5, 9, then pass by reference. Make sense? How that's working? So we're going to call this, if we in our find method, we are reassigning head to the next item in its list. We're going to find, when we find 5, we're going to return it. So then we're going to stop reassigning it. So head will be stuck at 5, pointing at 5 inside of our method, and then return, and then it clears out. We don't end up returning it or reassigning this version of head. We are changing the one inside of our method. If you want, I could rename this to something else just so that it makes a little more sense, but mainly that's what's happening. This is the local variable of find. This is, I don't want to really say find head, but whatever. This is the find head variable, and this is the main head.
That was already passed by reference.
Yeah, this is the main head variable. So they're different in scope, but their value might be pointing to the same spot in memory. That make sense, Mike?
Yes.
All right, let's see what happens. They want to take a vote or take a gamble on what might happen. There's no way for you to know what should happen unless you've run this before and tested it yourself. So don't expect you should know what's going to happen. Does anyone want to take a guess? Like gambling.
I want to say it's gonna put out 2859 just because we're working on a local scope, but I also don't understand exactly how this is working because I haven't worked with this stuff before. So that's just my blanket guess.
Yeah, it's something that happened that is more that I understand that is more understood in like the older languages because this is where it originated from. But yeah,
If I understand this right, line 17 makes display list and find, they're all in local scope. The whole thing, both methods are going to be in local. So that should alter it because both of them are in local.
kind of. So what it is, again, just to clarify a little bit differently, when you create like an int or primitive data type, your variable there is pointing directly to where it's pointing to a memory address of where that data is. And so when you then send that data to another method, it actually creates a brand new spot in memory to store the exact same number. So then you have technically 2 9s in your RAM. One that's from main, one that's from the new method. And so when you change that second one, nothing happens to the one in main. That's a pass by value. We make a copy of it. In a pass by reference, we have the at memory address. And so we have is the variable head is storing a memory address. So head here is storing a 0x381, which tells it where the value and next is. And so then when we do the next.value, we then say, oh, go to 0x361 and modify this information or get this information. And then when we create the new variable, we actually get a new, the other head variable is equal to 0x361 as well. And so then we make a change to this variable. Here we say head.value equals 7. We go to the same memory address that the original one's pointing at, change this from 7 to 9. And so then head is still, then the original one is still affected. That's the concept of reference versus value. we don't send a copy of the number, we send a copy of the memory address.
Gabe showed us this a long time ago in JavaScript.
Which usually is not a big thing in JavaScript. It's not as big as it is in other languages, especially not unless you're dealing with these kind of data structures. But let's see what happens.
Yep.
Oh, cool. It passed by value. That's awesome. All right, I'm impressed. Go Java. I was actually expecting that to be a pass by value.
Well, fine came up as 5 and 9, so, oh yeah, so it did.
Yeah, it didn't, but it didn't reassign the main head. It kept it there. So I'm actually impressed by that. Well done, Java. Awesome. In that case, yeah, then I guess in this one, we probably could also do the same thing here where all of it's head too. I'm going to say for safety mechanisms, and what you're going to see a lot in examples of this code is that a lot of developers will use the traveler because, again, this is language specific. Other languages will not do this. So you'll definitely see a lot more developers create a traveler just because that is the safety mechanism. So.
And again, some of them require more than one traveler, so it's nice to have trav 1, trav 2, and you have your different travelers, so you know where things are going. So.
Exactly. So I'm going to keep it as trav just because that is what you guys are going to see more in the wild. So I want to make sure you guys understand trav, but that's cool to know that if you want to, though, Java does do pass by value, not reference for that, which is really cool. So I was not expecting that. Nice. All right, let's move on to the last one here. This is the remove method. Again, if you haven't done, no, most of you have, but if you haven't gotten remove k elements from yet, this should at least give you a hint, because right now our goal here is just to remove the first instance of query. We want to remove the first instance. So again, same as what you did with the first 3 methods, what are we trying to do on this one? What is the process?
Traverse the list to locate the matching value.
And do what?
And splice it out of the list.
Yeah. Yep. Exactly it. So we're still going to do that whole concept of going through the list till we find the item we want, right?
Mm-hmm.
So it's really interesting here. We have a method that actually will find us the first instance of an item, right? And return to us that node, right?
Yeah.
So we could think, well, could I use find, right? That may be your first thought. Can I use find to make this easier? Well, let's think about this. This is going to be a little more interesting. That's not saying everyone here should have thought that. But I'm hoping that some people might have thought, maybe I could do this. Maybe I could use find to help me just grab the node and then I can just remove it. Because we know that find will actually give me the node. So let's see, we have our list here. We'll do our list. We have 2, 8, 5, 9. We have pointers, pointer, pointer, and point to null. And then head. So let's say we wanted to remove 5. Remove 5. So looking for that one. If we were to use our find method, we would do this, right? Let's see. Click on the mouse head. We do something like very simply node integer add node find head query. Right. And so now we have this bad node, which will do just bn over here. So bn, because I don't want to write out bad node. Where is that pointer going to be pointing when find finishes?
At the selected node, right?
Yeah,
Yep,
it should be
which-
pointing at 5.
Like that, right?
Oh, yeah.
So before we move any further, what is our list supposed to look like if remove works?
2, 8, 9, null.
Like this, right? Yeah. We want this is what our item should look like. So now seeing everything I have here available to me, how can I remove this 5 with this bn pointing at 5? Can I remove 5 in some way and somehow make sure, what happens if I remove 5 right now? If I just delete it or just like tell it, well, if I turn it to 0, that's not gonna do anything, right? It's still there.
Well, I mean, the thing about it is that find finds it, but there's no way of knowing like what the value before it or after it, or it's like you found it, but you don't know where everything else
Right.
is. It's
So
just like
again,
you
if we-
found it.
Yeah, and if you think back to what we were talking about, how do I actually remove a node out of a list?
You want to
We-
redirect the pointer of the previous node.
Right. I want to make 8 point to 9, and because of things becoming orphaned, 5 gets removed automatically. But when I'm looking at this, what I had here, the VN pointing at 5, not 8. Yeah, pointing at 5. 8 pointing at 5, 5 pointing at 9. Is there any way for me to access the 8 to tell it to point to 9 now? No, right? Because this is not a doubly linked list. I can't tell it to go back one. And if I had to think more widely, and again, think in larger sets, yeah, I know that 8's the second one, so I can just go head.next and tell the point. I don't actually know that this could be, but we actually know that the computer understands what the computer knows, that there's an unknown amount of items here, right? Our computer doesn't know how many items are here. It's a gray area. As a human, I know, but the computer has no clue how many items are in between the head and the node that find found. This list could be a 200 elements long, right? So that's one of the things we need. It's good to be aware of and be able to think about as a computer. Just because I can see the 8 doesn't necessarily mean that the computer can access it, right? At least not easily. So this is where, yeah, even though we have a method that can find us the node, it's not really going to help us. What do I really need to find? So now that we've seen that I'm now seeing the point where, yes, I can point at 5 and be like, hey, found you. That doesn't really help me to remove it. What do I really need to find? What do I really need access to in order to
The
remove?
value.
What's that?
The value of the next node.
Value of the previous node.
Yeah, value of the previous.
I think you need-
I know what you're saying, Mike. You're technically right. You're looking for trav.next is equal to what we're looking for, but what we want is, yeah, we want to be pointing at the node previously. If we're pointing at the previous node from here, I can now make the changes I want, right?
Yeah.
Because now from 8, I have access to every item I need. I can reassign 8 to 9 by saying, hey, 8, point at next.next. So I can tell it to point at the 9 automatically. So in a remove system, what I'm really looking for is the previous node. That's what I'm actually looking for. Now, again, I can't use find because I don't know what the previous node is. So I can't tell it to find 8. I may know it's the 8's previous node, but I don't actually know that because, again, the node has an unknown number of items in it. So we do instead.
But I would say that the find is good, because if you're going to try to remove something and if it's not found, then it's going to, if it's not found, then
If we don't
no
code it
sense
right,
removing
yes,
it.
of course, yeah. If it depends on how we code it, but that would just be an O of N to find out, should we even go through this, which means we're going to go through it a second time possibly. So we're going to do this. Let's go ahead and move my tablet out of the way. I don't need it, but I'll keep it plugged in case I do. Keyboard. Got our traveler, got our head, and we're going to do a while. We'll do the same thing here. While trav is not equal to null, as soon as we hit a null, we know we don't find the item doesn't exist anyway, and we should not remove it. So while trav is not equal to null, and now what we're looking for, we're not looking for trav.value not equal to query. This isn't right, because if with this, we will end up with the 5, right? With this code, we'll get the 5, which is what we used up here in find, right? What should this be? How do we change this to get the previous node returned to us? So that trav is the previous item. It's a slight modification to this will get us what we want.
Trav.next.value.
That's it. This is definitely what we're looking for. The downside, of course, of this is the potential again for a issue. What could this possibly be?
No.
Yep. So one last thing again, trav.next, not equal to null as well. But here's the funny thing about this, ready? If we're on our final node and it's not the item we're looking for, we're done, right?
Mhm.
So if our final item is not the item we're looking for, we're done. So we actually don't need this one. And so this is again that kind of concept that that can be a little confusing when you get into the best version of it. We don't need to run, we actually do in this one, or how do I want to word this? We don't need to run our logic on the last item, on our last guy here. So if we end up pointing at the last node, we could tell you, yep, the thing doesn't exist. It's not there. Because if we got to the last item and it is the node, we would have noticed the one before. So as soon as we get to the last element in our list, because of how this logic works, we can say, yep, it doesn't exist. So we're good. We're done. So first here, what I'm going to do now is do trav.next, trav equals. That's all our code does here. So if our trav.next is not equal to null, so on our line 2, it's not null. Oh, and it's not the value we're looking for, or its next value is not what we're looking for. We want to move to that item, right? Right. Hold on. Yeah, sorry. Yeah. So while our trav.next is not null, and while that item's value is not what we're looking for, so 8's not null and 8 is not what we're looking for, we're going to move over 1. And then we'll say, okay, well, is trav.next null? It is not. Is it the value we're looking for? Yes, it is. All right, this is what we want. We're now where we want to be. Let's see if this works again on the next one. Let's say we want to remove 9. Or on the 2, is our trav.next null?
No.
Nope. Is trav.next.value the one we're looking for? 9? No. So trav.next trav equals trav.next, we move to the 8. Is trav.next null?
No.
Nope. Is trav.next.value 9?
No.
Nope. So let's move again. Is trav.next null?
No.
Nope. Is trav.next.value equal to 9?
Yes.
Yes. And I'm at the spot right here where if I want to remove 9, I just tell 5.next to be null and I'm good, right? Which means I can point to null. So I can easily remove the 9 from the list by being here on the 5. Let's check to make sure we'll get what we want when we're looking for something that doesn't exist. So we'll do a query of
What about the first
7.
one? When
Oh.
we want to remove 2?
I was going to ask that too.
Good question there. Yep. 2, and that's something we're not checking for yet. Yep. But that's of course a special case scenario. Yep. Yeah. This won't work, right? Yeah, because trav.next not equal to null. It is. We're gonna where it is not null and it is not the value we're looking for, so we're gonna move. Yeah, we're not checking to see if our head is at. So yeah, when you're doing a remove system, the head is what we call an edge case.
Oh.
Yep, one of the rare scenarios. So the more common situation for us is that we're going to deal with somewhere in this part of the list, right? Most commonly, we're going to hit somewhere in the bulk of the list. But once in a while, yeah, we'll hit the head. That's going to be one of our edge cases. It's one of our rare cases or less likely cases to happen. Less likely, but it is something that can happen. That's an edge case. Chat. Oh, cool. Taylor's eating. That was a while ago, I'm sure, though. So what I'm going to do here is probably add some code here saying head first. Do that as a to-do. Once we realize that our current logic that we're coming up with that's trying to solve everything, we realize, you know what we come up with is definitely solving the majority of our situations, but it's not solving that first one. I think that's just a special case that we can handle specially. Now, yes, as you come up with it, if you figure out a better way to do it, go for it. But in this situation, I think it's pretty safe to say, yeah, we probably would just want to do a special scenario when the first item's there. But so let's continue on with this though. So now we have this. So trav is now pointing for add node. How do we remove it again? So how do we remove it? So we're pointing at the 5, we're pointing at the 8. We want to remove the 5. So what do I do to this node? So what do I move to the, what do I do to 8, which we know is trav? How do we change trav to make sure 5 is removed?
Trav equals next dot next.
Trav equals?
Trav dot next equals.
No, Trav, yeah, Trav. Oh, dot next.
Equals what? So what should trav dot next equal? We want trav dot next to equal the 9 node. How do I point at 9?
So it'd be Trav dot next dot next.
There it is. A little dizzying, but
What happens if
Where's,
trav next is null though?
that's fine, because that means
That is
it's-
fine?
So, well, look, if we're trying to remove the 9,
Mhm.
5, we want, in order to get rid of the 9, we want 5 equal null. So we go 5 is point is now 5 dot next is equal to next dot next null.
Okay.
We'll actually end up pointing at null, and so we'll nullify the pointer.
Yeah, because you can either assign it to a value or assign it to null.
Assign it to a node, to another node, or to null. Yeah, I try not to use the word value because value is one of our fields.
Sorry.
No
Well, yeah,
worries.
node, yeah, to a node, yeah.
Yeah.
It produces
Yeah,
null
'cause-
exception.
5 dot next is 9 dot next is null. So if we, so this line here would do 5 equals null. Or 5 dot next, sorry. Equals null. See how that works? Yes, this will work at removing any nodes in the main part of the list, the everything other than the head. So now let's add in our edge case. So if head dot value equals 3, what do we want to do? So think about this. Yes, in the situation where we're trying to do remove 2, what should our list look like after we remove 2? Is the best way to visualize what we need to do in our code.
Shouldn't it start from the head following? So head equals head dot next.
Yes, that is the code, but I want to make sure people understand why that's what we need to write. So what's
we have
how does our list look after we remove the 2? What should our list look like?
859.
859.
Yeah, we're redirecting what is referred to as head, what head is
And
pointing to.
head, yeah, and then our head, so our head becomes the 8. So we want, if we visualize it here, we're doing, oh, head should point here instead. And that's how we change our list, make sure that the 2 gets dropped. So, yep. Taylor, you said the code, but I want to make sure everybody understands why that's the code. So yeah, we're just going to say, oh yeah, if our head's the item we're going to remove, we just need to change our head then. We want to lop off our head. So we're going to do head equals head dot next. And I don't want to run the other code below this, do I now? I've done what I want to do, right? So how do I stop early?
Return.
Return?
You can return on a void, just return with nothing. You don't return anything. That's all. You just return control if you want to hear about it. Remember, the return statement always returns something, no matter what. In most cases, 95 to 99% of the time, you're returning a value plus control back to the previous method. In your voids, when you hit return, you're returning just the control back to the previous method that called it. So return always returns something. It always returns control back to the previous method. Sometimes, though, it'll include data with it. Actually, most of the time we'll include data too. More commonly than not, you're returning data. But no matter what, 100% of the time, return always returns control back to the previous method. That is our stuff. So let's go ahead and run, so let's go ahead and make sure these all work. So what we'll do next is go ahead and go back to our mouse. Let's add some of these items back here. So for, not there, here. Display list head, we'll go ahead and find. So we'll do again, display list head, oh, no, not that. Find. Do 5 again. Do the same thing again. I'm with 8, just make sure that both work. Let's go ahead and remove
You gotta put head
Five.
in for.
Yeah,
the
don't forget to
finds.
put that your find call.
Yeah,
You. Find head query 8. We'll do a remove head query, and we'll also then do another display list. Head. And we'll do one more remove 2. Display list. Okay. And display list again.
put head on 17 also.
Yep, I do. All right. So to confirm what we should be expecting here. This we should see the 2, 8, 5, 9 fit. Now let me know. On this one, what do we expect to see?
Two, eight, nine.
What is it?
2, 8, 9.
2, 8, 9? Really? That's display find, isn't it?
Oh, never mind.
65.
Just the 5?
And the 9?
Or display list takes the node that you're given and then displays anything after it as well. Remember?
Oh,
It's
okay.
just
so
using
yes,
that node as
9.
the head of its display list. So yes, this is going to
Oh,
display
okay.
5, 9.
Yeah,
What's
5.
this going to display? Think about what I just said. So, Jim, don't say what the answer is. Someone else. What is this one going to show?
5, 9.
Yeah, Leah got it. Yep, and so did you. Yep, you both got it. Good. So remove. Are we going to remove? Is not going to display anything, right? Nothing will display. So nothing here. However, after the remove, what should I display now? Display.
8 and 9.
There we go. 2, 8, 9. And after this one, which we get left? What's our last result?
8, 9.
There you go. This vicinity check, make sure we didn't break anything. We'll do another add node of, let's say 42, just because we have to include the universe and everything there, and put the head back in. And if everything works, what should the final result be?
8, 9, 42.
And I'll put the comma there just because we know we're going to see commas, but I haven't put them above. But for this one, we'll just clarify we should see a comma there. That the 42 should be on its own. So this is what we're expecting. Let's see if we actually get that. But what I'm doing here while this is preparing to run, did I actually click it or not? Oh, I did. Yep. I was going to say before I printed it, that was actually fast. Yeah, 2859. We got our 59, but we didn't actually delete anything out of it yet. We probably should have done a display list before, but it's fine. This proves that we didn't lose anything. 859. Then here we see, yep, the 5's gone. That's not expected. That's not right. Oh, right. Oh, right. I forgot about that now. We have a problem.
It's passing it in, and it's not actually modifying the main
No,
head.
it's
when we do
not.
that.
Damn it.
I was waiting for you to catch that.
Pass by reference is messing with me now. Damn you. Pass by value is messing with me. Damn you, Java.
Oh, it was so cool a minute ago.
Yeah, I know. Damn it.
Problem, isn't it?
Yeah, it is. Trying to think.
If you just do a system out on the method, that should give you the result, right?
The main point, the problem is here, we're trying to get the system to remove that head. Because of pass by value, it's not gonna.
Do we have
Oh.
to? Do we have to make entirely new nodes and put the values of the old nodes in and return the new node?
I'm trying to think what I'm gonna do. Yeah, I'm trying to think.
Because we have to extract the data, but we can't modify the original one within the scope of this method.
1 second.
I think Matt's right. I think you could return a new node that starts out by pointing at the at head.next.
And just use the find method and then point that as the head.
I'm thinking right now. So what am I coding? What am I typing here?
trying to figure out how to do it
So,
because
well, I can tell you how to do it. This is one way to do it. So we're going to return a node integer,
okay.
and no matter what, we'll always return head. So right here, we will return head.
Okay.
Here, instead, we're going to return the new head that we just created because we reassigned heads. We're going to return this updated local scoped head. Same here. We're returning the local scoped head, but in this version, we never changed it. So we're still returning the original version, original reference. And then whenever we do the remove item, remove will always do head equal. I'm trying to remember if there's a way to force a pass by reference. Like in other languages, there's a way of using like a symbol like a star or an ampersand. You can tell it, hey, pass this by reference. Do not pass the value, pass by value, pass by reference. So certain languages do have a way to do it. Yeah, can't remember how to do it, but it's fine. This will work too. This is why, again, it's good to know what your language does. Because yeah, I thought Java passed by reference there. Dang it. Make me look bad. It's called by value only. All variables, object types are actually pointers. Yeah. Interesting. Yeah, let's play that and see if that works. Now, this should work. There it goes.
Make sure mine does.
Look at that. So it was actually a really good thing that I did cover the pass by value versus pass by reference issue. And now I think I understand why the remove k values on code signal had you return the head. So now it makes sense. That's the best way to ensure whether you pass by value or pass by reference, regardless of which one your language does, you'll get the behavior you want. This is the way to handle when you don't know if it's passed by value or passed by reference. It doesn't matter because we're just reassigning it anyway. We're forcing it to be destructed. And even if it was a pass by value, a pass by reference, we would be returning the new updated head anyway and just reassigning it to what it's already equal to. This would work in both directions, regardless of what language you are using, whether it's passed by value or passed by reference, doesn't matter. In this system, we're saying yes. And here we are overwriting the head because we are actually giving back a new item. In a pass by reference, we've already modified head inside of here. We're just telling it now to just make it equal to the same thing we already modified. So the idea here is that we're enforcing a pass by reference now. Fun. All right, that was interesting still, but yeah. Slight modification, but there we go. It all works now. What we want to see happened, and that's what we want in the long run. So, and we did get the little extra knowledge of pass by value versus pass by reference. And Java, apparently a majority of behavior of Java is to do a pass by value process. So most situations with Java, apparently, now that I looked at it again, so I can remember, it appears that Java 9 times out of 10, or at least Java prefers pass by value. Based on what I just read. So, cool. Good to know. Any questions? Good. All right. So pretty much now you have all the kind of tools you need to really to play with a list. So you have all the tools on how to move around on lists. The last thing I'm going to make sure I mention, by the way, is with recursion. So a lot of these items, we can use recursion on a lot of these to kind of get through and go through it. On several of these, not all of them, but several of these we can. Recursion, for all intents and purposes, is just a looping structure where you're telling it to, hey, do the exact same thing on the next item of this. So when you're doing the exact same thing on items, you can pass the child item and tell it to do the same thing. And then after it's done doing the same thing on all the children, it could just go back to the chain and return. Recursion, though, has another system, and we're going to really dig into this next week when we get to binary trees. The real power of a recursion system is to be able to do additional information as you go back up the chain. So during our normal looping structures, most of our normal looping structures, it's a one-way road, right? As we go through our list, we go through one way and we're done, right? Mm-hmm. When we return, we go back to the original method up here. On a return in a when you see the return statement inside of a recursive loop, it goes back to the previous iteration of the loop, not to the previous method that called it. Remember, we're now doing multiple methods. Return returns out of that method, but since you're calling methods, return only breaks out of that one method. And so that's where the difference of a looping structure that we see here versus a looping structure recursion. So let's do something slightly different. Let's do a matters, but I don't know why I did that. Sure, not that. Rec add node. This is a recursive add node. All right. So what I'm gonna do here is we want to again get to the last node, right? And then add it on. And then return the head. Right? Yeah. Last node. Okay, actually, what do we do here? We only add the value as a new node onto a node with a next equal. Right. That's what we're looking for. We only want to add our value to a node that its next is null, unless the head is null. So we're going to simply say if head is equal to null, turn. This is what we did in our previous stuff. We had to do that. Turn new node. Else here. So otherwise, if it's not that way, we're going to go ahead and do turn rec add node. In my head right now. Do head next. I'm going to do it right actually. Hold on, try to think now. Let's think about this for a second. Make sure this works. Something similar. It's very close, but I think I'm wrong on this. Something feels wrong in my head. Where is my pen? What did I do? There it is. So in the first situation, we get our 2, head is equal to null. So we're going to return our new 2 node. And that's going to be head equals that. So now we come in with the 8. Head is not null. And so then we're going to do, hey, okay, in that case, let's go ahead and pass and do another version of right. I know what I did wrong. Yeah, I know it. I know what I need to change in my code. I remember what I forgot. I didn't have my notes up, so I'm like, what did I forget to write? So what we're going to do here now is going to go ahead and call again another version of the same method. So now I'm going to call another version of the methods we have. Right now we have this instance of the method, add node 2, 8. We see here that our 2 is not null, so we're going to go ahead and do a rec add node. What is head.next? What is that equal to?
8.
Not yet. I'll go here. Head.next is equal to what? We're trying to add the 8.
It's null.
Now,
Okay.
We do a null. 8 is our second instance of this recursive add node method. And so now we say, oh, yep, okay, head is now null. So let's go ahead and create the 8 node, and we're going to return that. So this gets returned back to this instance. So we get back on it, this 8 node. What is this line here now doing? What's it going to return?
It's not going to get to that line.
It does. It goes back to it. Remember, whenever you see a statement like return and then a method, this stops until this method finishes, and then it's going to be replaced by whatever's returned. And so what happens under the hood is that this gets run and evaluated. This gets replaced by the 8 node. So then what happens on this line then? What do I get returned?
Would it be another 8?
Yeah, I get the 8 keeps going back up the chain. The 8 gets returned again, which then means if we do that thing like we did before, where we are expecting the head to be returned, our head's going to get reassigned to the 8. Remember how that happened in our first version of add node? Same thing. I just want to make sure we go through the same process here. So we still have this issue where we're now accidentally overwriting our head. So that same issue here. So there's something missing on this line, right? We need to do something else on this line, on line 51. Want to know what the code we're missing might be? Any guesses?
Is that head dot next equals?
Right. Yeah, we don't want to return that node, but we know that at some point, this method, we don't know how long it's going to take for this method to do it. We know that at some point, this method is going to return us a node. It's going to give us some sort of node. And it's supposed to be the node that comes after my node, right? Whatever this returns should be my next point, my next item. And so I'm going to do head next equals the new node here. I'm going to return that. And we're going to return head. I'll now show you how this works. So now we got this one. Let's go ahead and add another one now. Let's showcase. So we added so this now gives us 2. So we got the 2. So first time we run this, we get the 2. We know how that works because this runs. So we know that works. What's actually happening in main? Let me go back up to main quick so that you know what we're actually doing quick. Add node, there we go. That's what we're doing here. We're doing multiple versions of the add nodes. The very first time this runs, writing 2, then 8, then 5. So let's go ahead and see how these work. So we clear. All right. Scroll down enough. So first time we run this, we get rec add node. Okay, head right now first. Head is null. So rec add node. We get null, comma 2, right? First time we run this. So we go through the code, we see if head null, is it null?
Yes.
Yeah. And so we create the 2 node and we return that out of here. And the return goes to main. So then we can reassign our main from null, our main head from null to 2, that node. So now let's run it again. So now we do rec add node. And instead of doing null 2, we now have head, which we know head is 2, the 2 node, and we're going to add 8. So is head null?
No.
So I'm going to do head.next equals rec add node head next. We've got the next call, the recursive call. So rec add node. And this time we do 2.next. What is 2.next?
No.
Yep. Null, comma 8. This node now says, okay, is our head null?
Yes.
Yeah, our local head is null. And so we then create the 8 node, and we're going to return that 8 node back to this rec add node to 8. And so this gets deleted. That method instance gets removed from memory, but it's still on the line of, so rec add node to 8, this line 51 here of this instance of the item is still running. So the 8 is still in memory, still in cache. We haven't lost it yet because cache still has it. We're now going to assign it to head.next. And we know that this head right here is 2. So we're going to say 2 to point to 8. See how that works? And then we return the 2 back to head. And so head gets pointed back at what it's already pointing at. So 2 is already being pointed at. Now 2 is now pointing at 8, an 8 node. Next iteration, we have the head node of 2, and we're adding 5. Is our head null? Nope. And so we say, okay, head.next equals rec advent node. Add node. What's the 2.next now?
8.
It's the 8 node, right? Comma 5. Is our head null?
No.
All right, it's 8, so it's not null. So again, we're going to run this line again now. So we're going to add another instance of rec add node. So rec add node. What is 8.next?
Null.
Now we got a null, comma 5. So is our head null?
Yes.
Sanity check there. Make sure we're all on the same page. So it is. So now this instance of rec add node is going to create our 5 node. And now that's going to return up to the rec add node 8. We're going to tell it, right? We're going to tell this 8 to point at 5, right?
Mhm.
Because the head.next. So head in this case is our 8. Even though we know our global head is 2, or our main head is 2, this instance of rec add node, the head is 8. And so 8 is going to point at 9. What gets returned though?
8.
Yes, that 8 gets returned. What the heck is going on there? Anything important? Nope, not important. Good. Okay. Yeah, we returned 8 back up to this instance. So I'm going to delete this and this. We see that the 8 gets returned. In this case, now we have this instance of rec add node. Now it's going to start running again. So now this rec add node now starts back up again on line 52 again. Sorry, line 51, and says head.next, which is our 2 node, is now going to point at what was returned. What was returned? Nope, what was returned from the
8.
previous one? Yeah.
8, sorry.
So we point at the 8 again, which it already was, but we're just making sure it continues to point at that 8 again. And then we return what? Yeah, our head, so 2 gets returned. And then it means our main head is going to continue to point at 2, which is already pointing at 8, which is already pointing at 5. And so we see how a recursive function-based system works differently than a for loop or a while loop, right? We see that we build these new instances of the same method that does the same thing, but eventually it goes back up the chain and picks up where it left off. Every one of those instances paused on line 51, right? Pauses on line 51 while the next iteration of it goes forward and does its thing. And eventually, at some point, it's going to go back up the chain where we actually do a little extra logic of assigning the current head to what was returned and then returning that head. And so we do a little more logic. But notice again how our return method, though, doesn't necessarily end the loop. A return method just sends us back to the previous instance of the method until we eventually get to the other one. Some terms that are important is that this guy right here, this guy is known as a special term for itself. And almost every single recursive system has to have this. Does anyone know what it's called? I don't expect anyone to because we've never talked about it, but I'm just curious. Anyone know what this concept of a recursive function is called?
It's a base.
case.
Yes, 2 people know. Nice. Base case is an inevitable line of code that will cause the system to go back up the line. It's the way to stop the domino effect. If you do not have a base case, what happens?
Infinite.
Or what is potentially, yeah. You have the high potential of hitting an infinite loop. And
Back
as
over.
you know, want to avoid those beyond all, you want to avoid those at all costs. So you always need, so yes. Now, are you limited to a single base case?
No.
Not at all. Yeah, you can have multiple base cases. The main thing is just that you should have at least have one base case that will always trigger at some point and start that chain back up the line. Yes, you can have multiple different types of base cases that cause that return to start happening.
You need an escape hatch.
Exactly. Yep. You need an escape hatch when you're dealing with recursion, just like with looping structures. All looping structures also need some sort of way out of the loop. You need to get out of the loop at some point. I will say with recursion, that's needed more than like a while true loop. Like a while true, we can just use break to get out of it. Then we're instantly out. That's our escape hatch there. But with a recursive item, we know that break doesn't work because it's not a looping structure that is recognized by break or continue. So break and continue do not work in a recursive loop. Return, and like I said, return Doesn't do what we're used to. Return won't end the loop. Return just sends you back one iteration of the loop. So these are the things you have to be aware of when using recursion as a looping system. It's a
You don't
little
wanna see-
easier. Yeah, it's a little easier to fall into an infinite loop. It's a little more difficult to get out. And as you saw right there, it definitely uses a bit more memory because I'm spinning up a new instance of every method.
You don't want to be in the ground. You don't want to be Groundhog Day.
Nope. Very true. Yep.
That's what I was wondering, because eventually if you get a set of data so large, it could cause a Stack Overflow with this type
Mhm.
of solution, right?
Yep. 100%. Yep. Stack Overflow. Great use of that. Yep. Stack Overflow. Yeah, you can easily run out of memory with it's a lot easier to run out of memory with a recursive loop than it is with a for or while loop. One of the things you'll see a lot of times is, depending on the interview and who you're interviewing with, throwing recursion out does not necessarily make you look good in all situations. Using recursion is good if you feel like they're giving you the problem because they want to see if you understand recursion or know of it. So just because you get just because you get the equation or the algorithm to factorialize or factorial doesn't mean you should instantly go to recursion unless you're getting this feel from the interviewer that they want to see, do you know recursion? Factorialize, for me, I feel is a horrible way of showing recursion because it makes people think that it's a good solution for recursion, for factorial. It is not. You benefit nothing from it, and it just uses up a bunch of memory. You could just use a while loop.
But it's pretty
or
simple. It's in one line, like almost like very simple code. And
Yeah.
it's down to one.
And
but-
it does at least help people to see what factorial is. It helps people to know that, and it's a great entryway into one of your first Google jokes. Matt, you look confused. Do you not know what I mean by that?
Oh, right. I forget what it is that you have.
Oh, not
but
that
it
one.
just does it again.
If you Google recursion,
Yeah.
Where is it? Oh, I actually didn't spell it right. Version. I'm not spelling it right. I'm not.
I like the math trees on the
There it
picture
goes.
of the side there.
Yeah.
Yeah,
Did you
so-
mean recursion? Yeah.
Oh, are you kidding me?
Yes, sir, Joe. That's what it does. Yep.
And the funny thing with this is if you click the back button, it'll take you back to your last search of recursion too. So it doesn't break you out immediately.
No, it is 100% a recursive system. Yeah. This is 100% a recursive system. We are now stuck in a deep recursion stack. So as I keep returning back, I'm returning back to the previous search of recursion. Oh, that's fun. Have fun, Richie.
Nerds have too much fun.
Yep. The main thing I like are these simple ones, the ones that are so easy for the everyday person to completely miss. Like the everyday person coming and doing this and be like, okay, well, I don't get it. But once you're a developer, this is just great. And you just love showing other people it now. The next time you get a chance, you'll be like, I want to show somebody something funny. And then you'll show a family member that's not a developer, like, yeah, and I'm like, never mind, you don't get it. 100%, this is straight up recursion because yeah, you could just keep clicking backwards and keep clicking in, you'll keep going back and forth. And that's again, what's really cool about it too, is that concept of, yeah, I can click a bunch in to keep going down the tree. I can go back a couple times and then start a brand new branch by just clicking on them again. Because then I lose that forward. As soon as I click on it again to go down again, I lose all that other forward branch that I had before. And that's really what happens in recursion. Again, we're going to see that definitely as we get into the trees. As we get into binary trees and get into binary search trees, you'll start seeing that. All right, with that, it's 8:30. We lost one person already. We'll probably actually just end class early today because we're gonna have low today. So that way you guys can work on projects, work on your algorithms. Yeah, we'll probably do that this weekend because yeah, I want you guys to really get a good amount of practice on this stuff. Feel free to meet up and get more practice on algorithms. Do some of the older ones if you haven't solved those either. Feel free to go back to the previous ones. Challenge yourself. Again, really just practice these items. Like I said before, just main thing, practice your computational thinking and approach. Solving problems first without writing code immediately. I'm trying my best to show you all these different ways I use my pen and paper, my touchpad, my trackpads and stuff to approach these problems and how I walk through them and solve them and approach them. So you see how many different ways you can approach a problem. before even getting into the code. Because I cannot stress it enough, and this should be a motto for yourself. You maybe help put it on a sticky note on your wall for all I care. Code doesn't solve algorithms. Thanks, phone. Code does not solve an algorithm. It will never do it for you. Code will never solve a problem. Code will never solve an algorithm. It is still up to the human to come up with the solution. All you're doing is instructing the computer how to then perform the solution. So 100%, you need to be a problem solver, and that's one of the I think is one of the biggest misconceptions about software developers and programming in this industry. Is people are afraid that you have to know that you must know code to solve problems, and you can be a good developer and be great at developing websites and all that stuff, but be horrible at solving algorithms. And while that's okay, the problem with the industry right now is that the way you test to become a developer for websites is to solve algorithms. And so I feel like there's a bit of a loss there, is that sometimes for some companies, they do a huge algorithmic test, even though you're not going to be doing a lot of algorithms on the job. You're going to be building websites and building full stack applications. So there is a disconnect there sometimes, but the main goal, of course, for you guys is to get good enough to be able to pass the algorithms for the interview and get into the job. From there, you'll learn you'll be able to do what you need to do, and you'll do some algorithms here and there. Don't get me wrong, you will have to solve some algorithm jobs, but usually not in the beginning of your time there. You'll learn, and you'll also have a team that can help you come up with the solution. No one's expecting you to come up with PageRank on your own nowadays. If no one knows what that is, please do some more Googling. I don't even know, chuckle on that one.
Nobody came up with that. Say that again.
PageRank.
PageRank. I said, if you don't know what PageRank is, Google it, because it's Google's thing for searching. PageRank is Google's algorithm. That's what made Google Google. Yes. That was my, oh no. I was like, that was funny. It was a great little like kind of thing. Oh. I guess I got too geeky there. Damn it. So yeah, no one's expecting you to create algorithms like that on your own. I don't even think Google themselves didn't create it on their own. I think two people, at least the minimum 2 people came up with that. Might have even been more, but I know at least 2 people were the founders of Google, and they came up with PageRank together. So, and yeah, companies nowadays, you're not coming up with Google's algorithms or anything like that on your own. You're coming up with new algorithms for companies for new features as a team. So, but it still is important that you understand problem solving and how to be part of that problem solving team. That's part of the reason why we're also letting you guys do algorithm solutions as a team of 3 right now. Main thing is though, is do your best to make sure you're participating in the team. Sound good? Awesome. Any questions? Anything, any concerns? Anything anyone wants to bring up quick? Got 30 minutes before 9. Usually we've been going till 9:30 for the last couple of days for class. So
I gotta go sleep in the hotel right now.
Can you post that code, please?
yes, I'm
Yes,
gonna
I
post
was
the
gonna
code.
say
Yeah.
that.
Let me do that. Is that on the? Did I post this to GitHub yet? Let's find out. I do have an algorithms GitHub. It is not a Git repo yet. So get in it.
I thought you had like a ch12 algorithms already there. Maybe I'm wrong.
Doesn't seem like I do. Let's find out. GitHub. No, we don't have a ch12 algorithms repo yet.
Wow.
All right, let's do it now. ch12-algorithms. Yep, ch12 algorithms is available. Yep, I don't have one yet. Great repository. A. Plus. Paste all that in there. And it's pushed. ch12 algorithms. So it should be right at the top of my repo, which if you guys aren't watching or following my GitHub yet, what are you waiting on? So guys, feel free to give me stars, guys. Come on.
Are we supposed to give teachers apples, not stars?
You're talking about a software developer. I don't care about apples.
All right, fine. I will
Unless
send you a Pro 13. Cool.
I was literally just about to make that joke. You beat me to it. Damn it. Unless you send me a computer, but I'll take a Mac Apple. There you go. Then again, I don't think any software developer expects to get an actual Apple as a treat, because an Apple to a developer is much different than an Apple to a math teacher. And half the time, I think you guys are getting the job so you could afford one of those. Maybe after you guys get the job, you can send me an Apple.
Isn't an apple different to a physics teacher? Or
Probably. They probably have something where like they're talking about like the existence of an apple. Is an apple an apple?
I was also thinking about the apple because of gravity.
Yep. You only give them an apple if you drop it from a high distance.
Yes.
To lob it at them so that gravity takes its effect. Any other follow-ups? Any other questions? So that's now pushed. I'll try to get both videos from Tuesday and today up on YouTube as soon as I can. Go ahead and stop the recording then.